Up, minus 20 grams. Come down to nothing. Here we are now with a levitating magnet. We'll have two sets of wire coils. We get an anti-gravity effect of about 26 grams. In other words, the magnet is 26 grams lighter than it would be sitting below. When we turn off the power, the scale goes back to zero. Up, minus 20 grams. Come down to nothing. Here we are studying how to get anti-gravity effects from spinning magnetic levitation. We have two sets of 3-wire coils staggered above and below. Each of these is wired as UVW from a variable frequency device. Each of these will give 3-phase power in the same spin direction. And the scale is tiered close to zero. Now as we turn on the frequency, a central magnet 60 millimeters with about a 12 millimeter hole in the middle will start to spin and wobble. We don't see any weight change. But then, as we speed it up, still no weight change at 10 hertz. But then when we speed it up to about 15 hertz, or 20 hertz, now you see the magnet rises. So we get a big change of like minus 20 grams in terms of anti-gravity. Put it back down again, and it goes to zero. Up, minus 20 grams. Come down to nothing. Now we can also see anti-gravity effects with 3 sets of 3-phase wire coils stacked on top of one another. We've got 9 coils in total. The scale is tiered and a 60 millimeter magnet in the middle. We'll start it spinning with 3-phase power. And we get to about 15 hertz. It begins to rise up. No change of weight on the scale yet. About 20 hertz. Now we see a big loss of weight. Next is control. We're going to do the same experiment with only one set of 3-phase coils UVW wiring, and we'll look for an anti-gravity effect. The scale is tiered at near zero. We start the magnet spinning 10 hertz, no effect. When we hit about 20 hertz, it begins to rise up. Very little anti-gravity effect, almost none. Goes up and down a bit. You see a little of effect when it jumps up and down, however, there's no permanent effect because it's going in and out of the three-phase field. Up, minus 20 grams. Come down to nothing. Here we're going to measure the anti-gravity force on a scale of that 70 millimeter magnet which rises like a top. We have three-phase wire coils, two sets staggered to one another. When we turn on the power at about 5 hertz, the magnet starts wobbling. The scale is very close to zero. No effect yet. Then as we put more rotational speed, there's 10 hertz. A little negative effect, not much. Now 15 hertz. Not much effect from the scale yet. And when we hit the plastic up there, it'll knock the plastic forward. That's when we start to see anti-gravity effect. Minus 20 grams. It's hitting the plastic on top. Here we go now. We have a 60 millimeter magnet with a 20 millimeter hole in the middle, a ring magnet, which can wobble quite a lot. We have two sets of three-phase coils staggered. Three-phase power, we're going to turn it on at 5 hertz. The magnet starts wobbling, and we're going to zero the scale, so there's no weight right now. Now as we turn up the power, 10 hertz, not much change of weight yet. Still wobbling. 15 hertz, and then you see the magnet's gone flat on the top. Not much change of weight yet. As we increase the speed of going flat, now we're getting a lot of negative weight on the top. Minus 10. Minus 50. Look at that. Minus 50 grams. As you come back down again, the scale goes down to close to zero. Next, we can look at 3 layers of three-phase wire coils and a 70 millimeter magnet spinning in the middle. Scale is tiered. And as the magnet comes up, we see about minus 20 or 30 grams.
Thank you.